Now we introduce two very powerful and useful tests, ratio test and root test. They have wide applications and they are very powerful. So these tests are testing for absolute convergence of the series, and they are very easy to apply, and they can be applied to a wide range of series. They are not necessarily always the best choice, but they are very powerful, so that can be very useful. The ratio test is the first among them. So you will see how easy this is to apply. So we have a general series here with AK, which is not zero, and we compute the limit of the ratio of two consecutive terms in absolute value. So these are generic terms. If the limit is denoted L, then we have one of the three situations. If this limit is smaller than 1, then we say the series is absolutely convergent. When the series is when the ratio is converging to some number bigger than 1, or the limit does not exist, then the series is divergent. And if the limit of the ratio is 1, in that situation we cannot conclude anything about the series, and we need to use some other tests. So what is interesting here is that the application will be quite easy, and also we have, in the case where the limit of the ratio of two consecutive terms is smaller than 1, the series is absolutely convergent. That's very powerful. That means the series is also convergent. But also, when the limit of the ratio is bigger than 1, we can conclude the series is divergent. This is something quite interesting and new, because we don't have many tests that conclude the divergence of the series. We have test for the divergence, that's pretty much the only one. So now with this ratio test, we have another way of concluding that eventually series can be divergent. Important thing is that when the ratio converges to 1, so when the limit is 1, we cannot use this test to conclude anything. We will see some examples. This is the rewriting of the same result of the ratio test. So if the limit of the ratio of two consecutive terms is a number, so obviously positive because we have absolute value, positive number smaller than 1, then the series is absolutely convergent, and therefore the series itself is convergent. If the limit is bigger than 1, so any number bigger than 1, so 2, 7, 5, pi, radical e, something bigger than 1, or if the limit does not exist, because in some situations we will see that the limit of the ratio does not exist because the ratio is increasing forever. In that situation, the series is divergent. So that's good news. And then if the limit of the ratio is 1, we cannot conclude anything, and we need to use some other test. So that's very important to realize, because it will happen sometimes that the limit of the ratio is 1, no conclusion can be drawn, and we need to use some other test. Example why we cannot conclude anything using the ratio test when the limit of the ratio is 1. Here is an example of two different series. One is divergent harmonic, so series of 1 over n. If we apply the ratio test, so we have 1 over n, so a n plus 1 is 1 over n plus 1, divided by a n is 1 over n. So we have double fraction, we rewrite it. So limit here will be 1. Okay, nice. But we know that this is a harmonic series, so it is divergent. Let's apply the ratio test to the series 1 over n square. We know that this is a p series with p equal 2, so it's convergent. So again, a n plus 1, so it will be 1 over n plus 1 squared divided by a n. 1 over n squared, so double fraction again, we rewrite it. So here again the limit is 1. So you see the limit of the ratio in these both cases is 1, but one series is divergent, the other one is convergent. So that's why if ever we get the limit of the ratio equal to 1, we cannot conclude anything. We need to use some other test. Similarly with the root test, so here we have a general series again, and then we compute the kth root of the absolute value of the general term. So if, obviously this will be eventually a positive number, if that number is smaller than 1, the series is absolutely convergent. If the limit is bigger than 1 or does not exist, the series is divergent. And again, if the limit is 1, we cannot draw any conclusion, we need to use some other test. You see, these two tests are very similar, they have the same conditions actually. It's just the expression that is different. This is called root test because we take kth root of the expression and then compute the limit as k goes to infinity. This is the rewriting of the same thing, so the nth root of the general term of the absolute value, if the number we get is between 0 and 1, the series is absolutely convergent and therefore convergent. If the limit is some number bigger than 1 or limit does not exist, series is divergent. And if the limit is equal to 1, we cannot use this test to conclude anything, we need to use some other test. So what is important to realize is if the limit in the ratio test is 1, there's no need to try the root test, the limit will be still 1. And also, if the limit in the root test is 1, no need to try ratio test, it will not work, again the limit will be 1. So these two tests are a little bit related. They have similar conclusion steps. This is a summary of all the convergence tests up to now. We haven't covered the integral test, so we can ignore the first one, but all the rest we covered. So the p series, when p is greater than 1, then the series is convergent. If p is smaller or equal to 1, the series is divergent. Direct comparison test, limit test with its conditions, alternating series tests with the conditions, absolute convergence. So this is useful in some alternating series and also with the series that have mixed signs but they are not regular. Ratio test and root test. So you see the conditions and the conclusions are the same. Now, when do I use one? When do I use the other? In general, we will use, let's say, the root test when we have clear exponentials. You will see some examples when you have the same exponential over the entire expression. Then it makes sense to use root test. Ratio test is useful when we have exponentials, factorials, or mix of exponentials and factorials, or mix of exponentials and some polynomials. So ratio test seems to be a little bit easier to use in certain situations than the root test. Root test, we use it mostly if we have the same power over the entire expression. Then it seems more reasonable to use the root test. So we will see some examples. Here we have an alternating series. So obviously we could try to use alternating series test, but quickly we will realize that we have a problem computing the limit. So we will need to convert this into a function and struggle a little bit. So in this case, ratio test, here we see a polynomial, so polynomial degree 1, and an exponential. So as soon as we see this mixture, it is reasonable to use ratio test. So we need to compute the limit as k goes to infinity of the ratio in absolute value of ak plus 1 over ak. So ak plus 1, So here we have k, so it's going to be k plus 1. 2 to power k is going to be 2 to power k plus 1 divided by, so ak, so k divided by 2k. So in these situations we usually have double fraction, so we flip it, we rewrite it, and now it's easier to regroup terms and simplify. So we have here 2 to power k plus 1, which is 2 to power k times 2, so 2 to power k and 2 to power k will simplify, so downstairs we will have only 2 left, so that's what we have here. And then we have k plus 1 over k. So 1 over 2 is a constant, so we take it outside. The limit here is easy to compute, it's 1. So 1 times 1 over 2, so that's 1 over 2. So 1 over 2 is smaller than 1. Therefore, by a ratio test, we can conclude that this alternating series is actually absolutely convergent. So you see, in essentially 2-3 steps, we are able to conclude quickly that the series is absolutely convergent. Here we have another example with a mixture of factorial and exponential, so this calls for ratio test immediately. Again, we have double fraction, so we rewrite it, flip it. This will be systematic. These things will be easy to simplify. So e to power k plus 1, so it's e to power k times e, so e to power k will simplify. Here k plus 1 factorial can be rewritten as k plus 1 times k factorial, so factorials can simplify. So these situations are common and they are very easy to treat. So we have 1 over e, we take it outside, and then we compute the limit here. Now what happens, 1 over e is a number obviously. Here we have k plus 1, we need to compute the limit when k goes to infinity. So obviously this expression here diverges, it goes to plus infinity, therefore the limit does not exist. So it's necessarily bigger than 1, therefore the series is divergent using the ratio test. So again, whenever we see factorials and exponentials, ratio test is to be used. Now here is an example of a wise use of root test. You see, we have an expression and everything is to power k. So now we take the kth root and simplifies our life. So this is a clear case for the root test. The entire expression is to power k. So now the root test, we compute the limit when k goes to infinity of the kth root of the absolute value of the general term. So this is the general term, and we take the kth root, so k over k is 1. So essentially we get this expression here. So limit of this expression is easy to compute. We divide by k upstairs and downstairs, so we get 2 over 5. 2 over 5 is smaller than 1. Therefore, this series is absolutely convergent using the root test. So here it's much easier and wiser to use root test than the ratio test, because it would be a total disaster to use ratio test. It would be much more complicated for nothing. You see, with the root test, everything is under the same power, so we use the root test. It simplifies our life. Here is an example of mixture of factorial, and here is n to power n. So this situation is complicated a little bit, because n to power n, you could say, oh, let me use the root test. Fine, but then you will need to compute nth root of n factorial. Good luck. So root test, definitely not a wise decision. So we try ratio test in this situation because we have n to power n and n factorial, so we have a factorial and some type of almost exponential. So let's say we use the ratio test that seems wiser and it's easier to use. So an plus 1, so n plus 1 to power n plus 1 divided by n plus 1 factorial, then double fraction. So I rewrote it immediately. So now it's easy to simplify things. Very nice. So here we have n plus 1 divided by n, which is 1 plus 1 over n to power n. So that's beautiful, but now we need to compute this expression here. So there is a lot of work now involved to prove that this expression actually converges to E. How do we do this work? Well, normally, as in Calc 1, we need to convert this into associated function, use the log, compute the limit of the log. In that process, we will need to use L'Hopital's rule, then we get the limit of the log using the L'Hopital's rule, and then finally we take the exponential of the result. So that's a very long process. So this is actually, it seems like easy one, but it's not so easy. Now, the limit here will be E. Since E is bigger than 1, then by ratio test we can conclude that the series is divergent. Now, what if we are a little bit more observant here and we try to see what's actually the writing of the general term? Because we saw here it is very tempting to use the ratio test, it's not an issue, but here the last step requires a lot of work. Now what happens if we just observe the situation? We write the term here an, we did this long time before. So what we observe is that n over 2, n over 3, n over 4, all of these terms are bigger than 1. N over n will be 1, but all the other ones are bigger than 1. So I have n times something bigger than 1. So that's obviously bigger than n. So the general term is bigger than n. When n goes to infinity, the general term diverges. Obviously, it is increasing without bound. Well, that means that by divergence test, since the general term does not converge to 0, by divergence test, we can conclude immediately that this series is divergent, just by writing out the general term and observing that general term is bigger than n. So you see, in this situation, an easier test, divergence test, is much more elegant and easier to apply than the very powerful ratio test. So this is important to realize. Ratio test in this situation is applicable, it's fine, but this limit here would require a lot of work. Observing or writing out the general term here simplifies the process, and we realize very quickly that the general term is actually divergent. It doesn't go to 0, therefore the series must be divergent by test for divergence. So you see, test for divergence is very simple, elementary, and in this situation solves our problem in 2-3 steps. While the ratio test is very powerful, but here it will require additional work, and we need to do that work properly. So it is important to realize, yes, these tests are very powerful, but that doesn't mean that they are always the best test to use. Here in this situation, we have an expression to power n. So everything is to power n. So this calls for the root test. So nth root of absolute value of the general term, and this is easy to compute. So the limit is 2 over 3, which is smaller than 1. So by the root test, this series is absolutely convergent. So in this situation, root test is the easiest because the entire term is to power n. So now I will go quickly through many of the examples. You can take some time to analyze them, but this is just an easy application of the root test and ratio test. And there will be some examples where we actually have a simpler solution than using these two tests just by observation. So here we have an alternating series. So obviously you could try to do alternating series test, but it will be a challenge. You need to convert everything into a associated function in order to compute the limit properly, and then to see if the general term is decreasing, you need to compute the first derivative. So that would be a lot of work. just to show that this alternating series is eventually convergent or divergent. So it will be a lot of work. That's why we see here a mixture of exponential and a polynomial. When we see this, it is wise to use a ratio test. So these things will simplify a lot with the ratio test. Again, we have double fractions. So by now we start getting used to double fractions and flipping them immediately. So here the simplification actually, so we rewrite this a little bit. We divide by n squared upstairs and downstairs. So easily we see that the limit here will be 2, so the limit downstairs is 1. So 2 is bigger than 1, and we can conclude by ratio test that this series is divergent. So this is very powerful and very simple, you see. Another series where we have exponentials, 3 to power n, 2 to power n exponential, and a polynomial. So in this situation, when we have exponentials and polynomials, it is very wise to use ratio test. If we have exponential and factorials, also we use ratio test preferentially. Again, double fraction, we expand a little bit, and we have the double fraction. Here, what we see is we have 3 over 2, and then we need to compute the limit for this term, because 3 over 2 is a constant, it's not going to change anything. So the limit here will be 1. So we have 1 times 3 over 2, which is 3 over 2, which is bigger than 1, 1.5 is bigger than 1. Therefore, by ratio test, this series is divergent. So you see here we are able to conclude that the series is divergent, even though this is an alternating series. So as soon as we have the mixture of exponentials and factorials, exponentials and polynomials, it is wise to use ratio test. In many cases, it simplifies our life. Here again, you see we have minus 3 to power n, so I split this in 2 pieces, minus 1 to power n times 3 to power n. So this looks like an alternating series now. This is your term here. What we have, exponential, factorial. What do we use? Preferentially, ratio test. It is important here to pay attention when we use the ratio here, a n plus 1. So a n plus 1 here we'll have 3n plus 1, and here instead of n it will be n plus 1, but with the brackets properly written. Very important to write the brackets. Then we have double fraction, so I flipped it immediately. But this part here with n plus 1 is very important to use the brackets. Okay. So now it's simplification, 3 to power n plus 1, so that's 3 to power n times 3. So these two will simplify, 3 will stay. Here, this part will simplify a little bit, because we have, if we develop 2n plus 2 plus 1, so 2n plus 3 factorial. So what we see here is 2n plus 1 factorial. So this one will develop a little bit. So it will be 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. So that will simplify with the upstairs. That's why we have this expression at the end. So all of these factorials will simplify, all the exponentials will simplify. So we will have some cute numbers and cute expressions. So now computing the limit of this, it's easy, it's 0. So since the limit is a number smaller than 1, by ratio test, we conclude that this series is absolutely convergent. This series has only factorial, so obviously the easiest thing is to use the ratio test, even though we could use some other things like direct comparison test with the series 1 over n squared, but let's say here this is even faster. We don't need to think too much. Limit here will be 0, therefore by the ratio test, series is convergent absolutely. Here what do we have? Polynomial and exponential, so ratio test is calling for us. I just rewrote a little bit e to power minus n as 1 over e to power n, so now it's nicer. So now a n plus 1, it will be n plus 1 divided by e n plus 1, double fraction with n over en. So I rewrote it immediately, flipped it. So you see now it's easy to simplify. We have en times e, so en with en will go. We will only have e downstairs. And then we have n plus 1 over n. So this limit is easy to compute. It's going to be 1. So we have the limit of the ratio is 1 over e. E is approximately 2.7, so this is smaller than 1. So by ratio test, this series is absolutely convergent. Again, here we have factorial and exponential. Obviously, we need to use the ratio test. That's the wisest approach. Things simplify now. We have ratio is n plus 1 divided by 100. So as n goes to infinity, obviously the upstairs increases without bounds, so the limit does not exist. Therefore, by the ratio test, this series is divergent. Here again, what we have is a polynomial with some exponentials, pi to power n, and then 3 to power n minus 1. So these things can be rewritten a little bit. By the way, as soon as we take absolute values, the negative sign doesn't matter anymore. So here, even though it looks a little bit crowded, it's not a big deal. N will be replaced by n plus 1, pi to n plus 1, divided by 3 to power n plus 1 minus 1, so n, 3 to power n. And then the double fraction, I flipped it. So we have this expression, obviously pi over 3 is constant. Here the limit is 1, so the limit will be pi over 3. Now, pi over 3, pi is 3.14, so this is bigger than 1. So by the ratio test, we conclude that the series is divergent. Okay, so this is similar. Here we have a polynomial and exponential. So ratio test is something to use. Now here is an example, just an illustration. What happens if we try to use the ratio or the root test blindly in every case? So we already know when the limit of the ratio is 1, the root test or the ratio test, they are not conclusive. We cannot use them. We must use something else. But here, in this situation, if we try to use it, I just want to illustrate that we can complicate our life. Sometimes when we see the cosines, sine, tan inverse, things like that, it's maybe wiser to use a comparison test and see what happens. Because if we use here a ratio test, which is okay, let's try, we have some ugly expressions. So now we have 1 over n plus 1, fine. This will go to 0 eventually, but what happens with this baby? How does cosine n plus 1 times pi over 3 divided by cosine n pi over 3, how does this behave? Well, we need to study this. We cannot just conclude something. We need to do some serious work. So these are two consecutive numbers here, n plus 1 n. So we need to see what's happening with the cosine of two consecutive multiples of pi over 3. So that requires some work. So I did some work here just to illustrate, and then from 1 to 6, and then after that the cycle keeps repeating. So these are the values. So what we are comparing here is the ratio of two consecutives. So this divided by this, then this divided by this, then this divided by this. So basically two consecutives, we need to see what's happening with it. We need to analyze. We cannot just conclude stuff. So this requires work. Yes, ratio test is powerful, but look, now we are in a mess. So what we observed is that the consecutive ratio of two consecutive terms varies between 0.5 and 2. Okay, so the ratio can be squeezed between these two things. Okay, fine. Now the limit on this side is 0, limit on this side is 0. So by the squeeze theorem, the limit is 0. Okay, cool. Now since the limit here will be 0 and limit here will be 0, so that's fine. So the limit of the product is 0, so limit of the ratio will be 0. Now I'm happy person. So I can finally conclude that by ratio test this series is absolutely convergent. But look at the problems here that I have. I need to be very careful. Now what happens if I'm just observing that cosine in absolute value goes between 0 and 1? Whatever the argument, cosine in absolute value is between 0 and 1. Let's see what happens. Very simple. I need to divide by n factorial. Okay, cool, I divide it. So now, obviously, series of 1 over n factorial, that one is convergent. So by direct convergence, but direct comparison test, the series of absolute values here is smaller than the series of 1 over n factorial. So everything will be absolutely convergent. So just by observing this, I simplify my life. Obviously, we know that series of 1 over n factorial is convergent because n factorial is bigger than n squared for certain value of n. So now we flip it. So 1 over n factorial is smaller than 1 over n squared. So the series of 1 over n factorial is smaller than series, obviously these are positive value terms, is smaller than 1 over n squared. So that series is p series with p equal 2, so this one is convergent, therefore by direct comparison this one is convergent, therefore by direct comparison series here with absolute value here is convergent, therefore the original series is absolutely convergent. So it's much easier and simpler and straightforward to use direct comparison here in this case and absolute convergence test. So whenever we have these sines, cosines, tan inverse, it's maybe wiser to just take the absolute value and squeeze them. It might help us instead of using very powerful ratio test and then having a mess on our hand. So just be aware of the limitations. It doesn't mean it's impossible to use them, but it might just require much more work than you are willing to do. Here's just one more example. So we have n factorial, n to power n. So obviously we are ready to go with ratio test. Fine, let's go. Let's do. So here again we simplify and we have this to compute. Eventually one day when we finish computing we'll get that this limit is 1 over e. And 1 over e is smaller than 1, so we will conclude that this series is absolutely convergent. By the way, this is a series with positive terms, just to observe. Now, how do we compute this limit? Well, good luck. As in Calc 1, we need to transform this into associated function with x. Then take the log, because we have something to power x. We take the log, rewrite it, compute the limit of the log nicely. Limit of the log using L'Hopital. It's a little bit messy, and then we need to compute this limit is -1. Cute. Now we take the exponential of the limit of the log and we get our result. But we must do this work. We cannot just from here conclude 1 over e. Wow. We need to use associated function, do the proper process. So here now we need to take the log like in Calc 1. L'Hopital. So it's a lot of work. But it's gonna work, it's fine. We get that our series is absolutely convergent, we are happy. But a lot of work. So what if we are just wise a little bit and just write out terms? So n factorial is 1 times 2 times 3 times 4 times 5 up to n, and n to power n is n times n times m times n. So we just write it out just to see what happens. We observe that each of these terms is smaller than 1. 1 over n is smaller than 1, 2 over n smaller than 1, 3 over n smaller than 1. So the product will be also smaller than 1, obviously. Now for the purpose of what I'm doing, I'm just taking the first two apart, and then I realize that what is in the bracket is also smaller than 1, obviously. So this product, everything is smaller than just the first two terms, because this is smaller than 1. So something times some number smaller than 1, result will be even smaller. So that's what I can conclude. Now, why this is useful? Well, I just realized that my general term is smaller than this, but this is a general term for a convergent P series with P equal 2. So by direct comparison test, this thing here is convergent. So that's straightforward. Obviously these are positive terms, so it's also absolutely convergent because absolute value of this is also the same thing, because everything is positive here. So you see, just by using direct comparison test, by observing things, I solve my problem in 2 steps, compared to very powerful ratio test, where I need to have an expression and then convert it in associated function, take the log, compute the limit using L'Hopital, then take the exponential of the result to conclude something. While direct comparison test, just by expanding the general term, it takes 2 steps. So yes, ratio and root tests are super powerful, but that doesn't mean that they are always the best to use. Just be careful. So here we have again exponential, here is factorial to power 2 and then another factorial. So this calls for ratio test, it's fine. So we just expand the things. So 2n plus 2 factorial, so we expand it. And then we have 2n factorial, we'll simplify with this 2n factorial. So essentially now we have ratio of 2 polynomials, we compute the limit is 4 in this case, so by a ratio test the series is divergent. By the way, don't even think about root test in this situation because there's nothing calling for it. We have factorials. As soon as you have factorials, ratio test is the best option. Here though, we have something and everything is to power n. So now root test is a wise option. So we take nth root of the absolute value of the expression. So nth root and power n will simplify. So this now is a cute expression and we compute the limit. It's easier to compute. Obviously it's limit of ratio of 2 polynomials. It's easy to compute. So here it's 1 over 2, so it's more than 1. That means that this series here is absolutely convergent by root test. So here root test is a wise option. What happens here? We have minus 2, so we can rewrite it as minus 1 times 2. So this looks a little bit like an alternating series. Obviously when you take absolute value, the changing of the sign will disappear. So now what we see is we have something and everything is to power n. So root test is a wise option. Here the limit is 0, which is smaller than 1. So the root test tells us that this is absolutely convergent series. So this alternating series is actually absolutely convergent. So you see, it's very simple application, straightforward. Here again, we have change of sign and then ln n to power n. So we have something to power n, nth root. So basically root test is to be used. Here again, everything to power 5n. So again, nth root would simplify things. So root test is to be used. Now here the power is 5n. So it's going to be 5n divided by n. So it's going to be 5 only. So just be careful. So now we need the limit of this expression when n goes to infinity. So what happens? We compute the limit is 2 to power 5. So this is bigger than 1. So by root test, this series is divergent. So when you see that you have something, an expression, everything to a power n or some number times n, then root test is the best option. Here also we have some expression to power n squared. So again, nth root, but now n squared. So n squared divided by n, we will still have n. Oh, this is our old friend. We saw something similar. So to compute this, now the limit for this piece, because that's what the root test requires, with limit of this expression, well, we need to use associated function. The log and then the L'Hopital to compute the limit, and then take the exponential of the limit of the log. So this work is required. There's no choice here. We just have to do it. There's no point of even thinking about ratio test in this situation. Root test is the best option. But it requires associated function, L'Hopital, and then taking the log of the limit of the ln. So here at the end, the limit is e, which is bigger than 1. So this, by the root test, we see that the series is divergent. Here again, something to power n, so the root test, the best option. Now the limit here, what happens when the tan inverse n, when n goes to infinity? Well, the limit is pi over 2, bigger than 1, so the series is divergent. Here again, okay, same procedure. We have an expression to power n, so root test is calling. Here, this is an interesting situation. So this is an alternating series. Is it conditionally convergent? Is it divergent? Is it absolutely convergent? What's happening? By the way, if we try to use here ratio test, there's no point of even thinking of root test because there's nothing to power n. This is just change of sign. If we try to use ratio test, we will realize that we'll have ln of n plus 1 divided by ln n, and then we'll have n divided by n plus 1. So in both cases, the limit is 1. So we will have 1 times 1 is 1. So the limit of the ratio would be 1. So that means that the ratio test is not conclusive. So it's very powerful, but in this situation is not conclusive. So there's no point even to trying it. So how can we proceed? Well, this is now an alternating series. We could obviously use the alternating series test and see what happens. Just an obvious observation, if we want to have this as absolutely convergent, well, we need to compute this and see if is it. So basically the sign will go. Now here ln n is bigger than 1, obviously. So this series is bigger than series of 1 over n, which is harmonic divergent. So our series is bigger than a divergent series. Therefore, the series of absolute values is divergent. That means that this alternating series cannot possibly be absolutely convergent. It is not absolutely convergent. Okay, that's cool. Maybe it is just convergent conditionally using alternating series test. Well, we need to check the two conditions. Here again, we need to compute the limit properly. In this situation, we need to use associated function, L'Hopital, and to verify. Now, this application is easy. Now, to see if the general term is decreasing, we use the first derivative. If the first derivative is negative, then the general term is decreasing. So essentially, we need to see at which point this expression is negative. So downstairs is positive. When is this negative? When ln x is bigger than 1. When that happens is when x is bigger than e. So essentially, for n bigger than 3, our general term will be decreasing. So by alternating series test, we can conclude that this series is convergent, but we know it is not absolutely convergent. Therefore, we can say that this alternating series is conditionally convergent. Here in this situation, it's interesting to observe that we have polynomial, an exponential, and upstairs exponential. So we would normally think of the ratio test immediately. Now you can say, oh, this is an alternating series, let me try. Well, wait. It's maybe wiser to try ratio test. But someone can say, hey, let me try the root test because you see here I have n. Yeah, but here you have n also. So let's see what happens if you want to use root test. There's nothing wrong, but you will suffer because you have mixture of exponential and polynomial. Normally that's good news for the ratio test, not for the root test. But let's say you don't think and then you jump on the root test. Let's go. So it's easy, you'll get rid of this exponent, so you have 9 over 10 cute, but now you have nth root of 1 over 10 times n. So essentially you need to compute the limit here for this part because this is a constant. Good luck. So essentially you need to compute limit of n to power 1 over n. Good luck with that. So you see here, because of the sign, okay, we have minus, but now this is a struggle because you need to use associated function, do the proper work, which means now you need to use the ln of the expression, then use L'Hopital eventually, then takes the exponential to get to your limit. So all that to compute limit of this term, all this work, just because you jumped immediately on the root test because you saw the power, but you didn't realize that you have a polynomial also. So this work needs to be done properly. And then you conclude happily that the limit here of this expression is 1. Yay! So at the end, 1 times 9 over 10, so that's smaller than 1. We are all happy now, we are absolutely convergent. Beautiful. But how much work? But if I use wisely ratio test, because I have exponential, and a polynomial, when I have that combination, I need to use ratio test. That's wiser. So the general term is obviously the same, but now I do the ratio of the two consecutive terms. N plus 1 here would be n plus 1 plus 1, so that's why you have n plus 2. And then you compute now, computing limit here, look. Computing limit of this expression is piece of cake, it's 1. So 3 steps, I'm done by ratio test. So be wise when you have exponentials, so number to power n, and polynomials, use ratio test. When you have exponentials and factorials, use ratio test. If everything is to the power n, then it's wise to use root test, but otherwise ratio test is wiser. Here again I have exponentials and polynomials, so it's wiser to use ratio test, much faster. Here, now I have one expression, everything to power n. Okay, cool. So now it makes sense to use root test because I'm gonna get rid of the power here, and then I need to compute the limit for this. Cute. How do I compute the limit? Okay, you feel it's gonna diverge, but you need to do the proper job. So what do we do? Well, as usual, associated function. To compute the limit, we have infinity over infinity, so we use L'Hopital's rule, a little bit of work, and as expected, the limit does not exist because the expression keeps increasing forever. So this limit here is obviously not existing, but let's say it's bigger than 1, it doesn't exist. So it's not smaller than 1. In that situation, we know that the series must be divergent by root test, because we use the root test here, right? And then we had to compute the limit for this. So in this situation, we had no choice. This was the wisest option, and we had no choice but to use associated function and suffer a little bit. Again, the limit does not exist, therefore by root test the series is divergent. Here we have sine, we remember sines, cosines, tan inverse, maybe it's wiser to squeeze them. So these expressions change sign but irregularly. So it may be wiser to just try the absolute value test just to see what happens. So if we squeeze the sign in absolute value, it's between 0 and 1. Okay, so that simplifies my life. So the general term is between 0 and this expression here. So I have downstairs 1 plus. So this is bigger downstairs than just n root n. So the ratio will be smaller than this. So this is 1 over n to power 3 over 2. Wow, I recognize a p series with p equal 3 over 2, which is 1.5. Oh my god. So that means I'll compare the absolute series with absolute values to the p series with p 1.5 bigger than 1. this series is convergent, the smaller series must be convergent. So the series of absolute values is convergent, therefore the original series is absolutely convergent. So whenever you have these trigonometrics, sine, cosine, tan inverse, it's wiser to use the absolute value and squeeze them and see what happens, instead of trying root test, ratio test, and other gymnastics. Here again, alternating series, so this is just a sine changing, and I have tan inverse. Oh, I know that tan inverse when n goes to infinity is bounded by pi over 2. So maybe it's wiser to use just the absolute value series and then see what happens. So the general term is squeezed. I need to divide by n squared. That's beautiful. So now this will be my series, p series times a number. So p series with p equal 2. So this one will be convergent. So the series with absolute values will be convergent. So I'm now happy man. This alternating series will be absolutely convergent. So direct comparison test is simple but very useful. So especially when you see these sines, cosines, tan inverse, it's wiser to just take absolute value of the expression here, of the general expression, and then squeeze it. And then divide by whatever the n square or whatever the power of n, and try to conclude something. So yes, ratio test and root test, they are powerful, but trying to apply them here would be not wise at all. Here is one more example of what happens if we try hard stuff. So here what do we have? Change of sign, so alternating series obviously, and then root n ln. Again, if I try ratio test, because there's no point of even thinking of root test because there's nothing to power n. So ratio test here would give me 1. The limit would be 1 of the expression, so it would not be not conclusive. So I cannot use it even. Okay, fine, but this is an alternating series. So let's see what happens. Just an observation. If I take the absolute value, so I have this expression here. Now ln n is smaller than root of n. So if I flip them, I get this expression here. And then I'll need to multiply both sides by radical 1 over radical n to get my expression here. So I realize that this piece is bigger than this, but this is 1 over n, which is harmonic. So the series of absolute values is bigger than a harmonic divergent series. Therefore, the series of absolute values is divergent. Okay, cool. So what I just realized is that my alternating series cannot be absolutely convergent. That's cool, but that's important to realize because the question is find if it's absolutely convergent, conditionally convergent, or divergent. So I know that series of absolute values is divergent, therefore my series cannot be absolutely convergent. Okay, fine. That's cool. But now let's see with alternating series test what happens. Well, this one is straightforward. There's like just write it out. Obviously 1 over these expressions that goes to 0 obviously, and then these terms are decreasing, so the next term is smaller than the previous obviously because the denominator is bigger, so 1 over will be smaller. So alternating series test is both conditions are straightforward to verify, so we can conclude now that our alternating series is convergent, but we also know that it is not absolutely convergent, so it is only conditionally convergent. So those are some observations. Again, root test and ratio test, they are very easy to use, they are very powerful, but that doesn't mean that they can be used all the time. We saw some situations like this one. Ratio test would give you limit 1, so it is not conclusive. And also we saw sometimes we can use direct comparison to get our conclusion faster and easier. So yes, those tests, root test and ratio test, are powerful, but they are not almighty. So be careful, don't use them all the time just because. Be wise. Sometimes they're not as performant as some of the easy tests. So this is to be used wisely.